Okay, let's see. How do I, hmm. Stop. Okay. We are live now. I'm not sure how to edit this. How's the sound? Live now. Okay, sound is good. How to edit this? Sound is good. Sound is good. Okay, now let's move on to this. Put this right up here. Let's put this right up here also. Okay. And to watch this currently. So let's go full screen on this. 40% for the previous. Wait, so hang on a minute. Oh yeah, hang on a minute. So the question asks, to future improve the design, you need to introduce boosting algorithm that reduces the error by 70% in the first two cycles and by 60% in the subsequent cycle. Compute a new minimum Okay, let's start with the first example. Okay. So the first example here gives us, so we're trying to basically calculate a cylindrical cube optimization. We're trying to do a cylindrical cube optimization. And so we are given the fixed volume, 0.010 meter cubed. And then we have the initial sidewall cost. We have the initial end cap cost. Okay, let me just go full screen. We can do this right now. How do we how do I start? Huh? I want to convert the video. I just want to go um now how do I go to present mode? Uh how do we slideshow? Okay, okay. All right, all right, all right. Alrighty. What happened to the camera? Goddamn place. Okay. Not sake. Stay up there, okay? Just stay up, for God's sake. Okay. Why is it falling like crazy? What the fuck is wrong with it? Okay. Okay, hello, my name is Yarob. This is okay, so hello, I'm Yarob. This is a presentation for the engineering and mathematics assignment. So today I'm going to be presenting a few things actually. So the first thing we're going to be presenting today is the cylindrical tube optimization. So we're given a problem where we have a cylindrical tube to design and for a criteria to fit an A4 paper and basically a mailing tube, right? So how did we go about this? Okay, so first we were given a few things. So as we can see here, so we were given the volume, and we were given also the price. So the cost for the sidewall, and we have the cost for the end cap cost, or the initial end cap cost, the initial sidewall cost, and we also have the analysis case end cap cost, which is 35 ringgits. And we also we're trying to get the radius and the height. That's the goal, right? So besides that, we have the area formula for the volume, for the what the fuck am I saying? Okay, to over to you. Oh, okay. Let's run it back. Let's run it back. Okay, so hello everyone. My name is Yarob. This is an assignment for engineering mathematics one. In this assignment, we're going to be discussing a few things. So the first thing is our first task is to design a cylindrical tube. So this cylindrical tube need to be optimized based on its height and radius. So we're trying to get the most optimum height and radius for this tube for the least amount of cost. So we're given a few initial things. So we're given the volume, and we're given the sidewall cost, and we're given the end caps cost. So these are like the closing things, right, from each side. So basically, these will have the area of a circle as represented here. So we have the area which is 2 pi r squared. So two of these, since we have two of them, pi r squared is the area of circle. So 2 pi r squared for the sides, for the end caps, and we have the side area, which is going to be this, and we have the formula for the volume of the cylinder, which is the one represented up front here. Okay, so the volume of the cylinder can be also rewritten as, okay. So in order for us to figure this problem out, so the first thing we need to do is to isolate the h. Okay, so by isolating the h, what do we achieve? So we get the volume formula to write the h. Okay, so basically we have the volume is equal to pi r squared h, which is equal to the number we're already given. So since we are trying to find the height and the radius, we're starting with the height. Okay, so since we are trying to find the height, so we're gonna try to isolate it from the volume formula. And since we know the volume, we can just substitute the volume, and then it's going to be over pi r squared, and therefore we can just get the height, right? Very easily, very easily. And for this function that we see here, so this is going to be the function to calculate the whole thing, basically the whole optimization. So we have the cost per meter side, per meter squared for the side times the area of the side times the cost per meter squared of the end caps times the area of the ends. So we need to know the cost. We need to per meter squared for the end caps and for the side, and we need to know the area of the side and the area of the ends. So we already know the area of the ends, and we already found the h. So we already found the h, so we're going to use the h to find the area of the side. Okay. So as we can see here, like we represented this formula, so c is equal to c side and c ends. So this is the formula to calculate the side the sides, and then this is the formula to calculate the end caps. Okay, and we just substitute the price. So this is the cost. So 18 times this, so that we know how much are we getting per meter, or how much per meter's cost. And then this is for the sides, and then this is our final formula here. However, we still don't know the h here, since we have a h to figure out the side. We figure out the h using this right here, and the relationship between the volume and the height. So we can easily get the h here. We just substituted it, and then we just substitute it into the formula instead of like using the volume. Instead of using just a h, we just replace it with the expression that we got from the volume. So which is this expression right here. This is a representation of the height. Okay, and so we just substitute and we get this this form right here. However, we still don't have the r. Okay, the r is also missing. So in order for us to get the radius, so we try to first we need to take the derivative of this formula. So by taking the derivative, the derivative of this is gonna be this. Okay, so wait, something is wrong here. Okay, this should be 2. Okay, okay, my bad. This should be 2. Okay, so by taking the derivative, we're gonna get this. So the 2 is multiplied into here, and then we get this, and -1. And then same happens here, so -1, and then this is gonna be -2, okay? And then if we take it to replace the form, we take it to another form, we get this 0.36, and then we put this to the bottom, so it becomes positive. So over r squared, which is the same as the previous form that it was in here. So we just made it that way so that we can make the derivation easier, okay? So this was the first derivative. So next up, so we need to, in order for us to find the stationary point for the optimal radius, because we want the optimal radius, right? So for the optimal radius, we need to zero everything, right? So equating this formula that we got here to 0 will give us the optimal radius for the least amount of money, okay? So basically, we equate this to 0, we take this to the other side. So now it's positive, and we just, by simple replacement, we just take the r to the other side. Now it's r cubed, and I take this to this side. Now it's 0.36 over 112 pi, and then we just take the cubic root. We take the cubic root, forgot the 3 here. So we take the cubic root of both sides, and basically we get this, after calculating, putting all that into the calculator, we get 0.1 meter, okay, which is the optimal radius, okay? So this radius then is going to help us find the optimal height. So we just substitute it back into the formula for the height, so which was it's not in here, which is this one, right? So we substitute back into this formula, and we get the height that we need, and therefore we can find the C minimum, which is the minimum cost that we need by substituting into the first formula. Okay. So yeah, that's for the first problem. Quite easy and straightforward. So we got the radius at 10 centimeters, we got a height of 31, and we got a minimum cost of 5.36 ringgits. Okay, so the next problem is taking on a billboard wind load engineering, basically. So we're trying to basically calculate the center pressure. So a few things are given here. So we have firstly we have the width, and we have the height of the billboard, and we have the pressure relation. So we don't have the exact pressure, but we have the pressure relation. So we're gonna need to find the pressure, which is the main thing that we need, and we have the formula for the force. Okay. So obviously first we just substituting everything here. So we have the height. We use the height to find the force. So basically we substituted the height and the across the height across the billboard and the width into the formula that we're given here. So so after substituting that, we can use that to get our force. So doing just normal integration here. So we take this, since it's a normal number, we take it outside, we do the integration to this. Extremely normal integration here. We just substitute here with simplification, and then we substitute the numbers 4 and 0, and then we get the force in Newton. So this was for the pressure, for the force, right? And then to calculate the pressure, so this is the relation we're given. So we need the force, we need firstly the moment, okay? The moment divided by the force. So we already found the force, now we need to find the moment. And in order for us to find the moment, we just substitute everything back in again. However, we've changed some things here. So instead of directly, second. Huh? Okay, so instead of directly doing the same thing as we did here, so we're gonna replace it a little bit. So we're dividing this by 2, okay? Instead of not dividing it here at all. So we're dividing this by 2, and we're dividing this one by 3. So and the reason for that, so we need to know that the center is the center of the pressure should be higher than the geometric value, which is 2. Okay, so that's why we divided by 2 here. And yeah, so that's what happened here. on my screen. Oh, wait. Missing something. Okay, okay, okay. I see it now. Roll that back. Okay. Okay, what about the last question? P naught. P of y is equal to P naught. Constant pressure. The center of pressure would be lower. If the pressure is uniform, the force is distributed evenly across the surface, meaning the center of the pressure would act exactly at the geometric center. Act at the exactly at the geometric center, h over 2, which is 2 meters. H over 2, which is 2 meters. In the current case, uh, the pressure the pressure increases with height. Um, what? Got messages? Recipe is higher. The center of pressure will be lower since the pressure is uniform. The force is distributed evenly across the surface, meaning center of pressure would act exactly at geometric center, h over 2, which is 2 meters. In the current in the current case, the pressure increases with height. Hence, as in the formula, it's presented plus 12y. Okay, plus 12y increases the y-axis. Okay, by 12. Goes up in the y-axis by 12. Okay, y-axis. Yeah. Putting more force at the top and shifting the center of pressure upward to 2.25 meters. So Py is equal to P naught. Okay, so it's the constant pressure. Py is equal to P naught, constant pressure. And in this example, Py is equal to P naught, constant pressure. So Py is equal to P naught in this example, which is constant pressure. So Py here is equal to P naught for this specific reason, since this is constant pressure. Okay, it's constant, and so since it's constant pressure, the pressure is going to be distributed evenly across the billboard, right? And since it's 4 meters, right? It's 4 meters. If we divide this by 2 to find the center, it's going to be at the height of 2, right? Which is at 2 meters, right? But what we got here is 2.25 meters, so it's a little bit higher. Okay, it's a little bit higher. Okay, this kind of looks like a diffusion model, but anyways, yeah. So since it's higher here, it's not going to be distributed evenly, and since the pressure is uniform, the force is distributed evenly across the surface, meaning the center of the pressure would act exactly at a geometric center, which is 2 meters. In a current state, in the current case, the pressure increases with height. So in the current case, we have the pressure, okay, increasing with height, okay, going up with the height. The pressure increasing with height plus 12y, okay, plus 12y. So, and so, as we increase the height, the more the pressure we're gonna have. Right. That's one thing. So more force at the top. So putting more force at the top and shifting the center of pressure upwards. This is gonna apply more force at the top and shift the pressure, the center of pressure upwards. So the center of pressure is no longer here. It's somewhere up here. Yeah. And since this is a little bit up here, so it's not gonna be like balanced anymore. If we apply the same pressure, so therefore it's gonna be lower. So if the pressure here is higher, it's gonna be pushing this forward a little bit more than here. So therefore this is gonna be lower. Simple as that. Okay. Okay. Finding the smallest integer n, given e naught is equal to 5%. Our target is less than 0.5%. Okay, less than 0.5%. So decay rate, error is 60% of previous. So factor is 60. Previous error factor is 0.60. Boosted cycle reduction, 70% reduction. Factor of 30, okay? Factor of 30. And if we go beyond that, we need to use 60, right? Initial times 20 minutes. Initial times 20 minutes. Oh, it's missing some. Wait. قل لو أن تستعجل لقضي الأمر بيني وبينكم والله فاتح الغيب لا يعلم إلا هو ويعلم ما في البر والبحر وما تسقط من ورقة إلا يعلمها ولا في ظلمات الأرض ولا رطب ولا يابس إلا في كتاب مبين. وهو الذي يتوفاكم بالليل ويعلم ما جرحتم بالنهار ثم يجمعكم فيه ليقضى أجل مسمى ثم إليه مرجعكم ثم إليه مرجعكم ثم ينبئكم بما كنتم تعملون وهو القاهر فوق عباده ويرسل عليكم حفظة حتى إذا جاء أحدكم الموت توفته رسلنا وهم لا يفرطون ثم ردوا إلى الله مولاهم الحق ألا له الحكم وهو أسرع الحاسبين قل من ينجيكم من ظلمات البر والبحر تدعونه تضرعا وخفية لئن أنجيتنا من هذه لنكونن من الشاكرين قل الله ينجيكم منها ومن كرب أنتم تشركون قل هو القادر على أن يبعث عليكم عذابا من فوقكم أو من تحت أرجلكم أو يلبسكم شيعا ويذيق بعضكم بعض. مش هنصلح لك مرة تقرأها علي وتقرأها صح تجي اليوم التاني تسمعها مش بنعمل لك انت غايب 10 أيام مكتبتش consequences يعني خلاص هعوض لوحدك يعني مش فاضي نقعد نعوض لك أنا قديم نصلح لك لا صلح لوحدك مش معاش تغلط مش تركز مرة تانية معاش تغلط مش تركز مرة تانية معاش تغلط لا مش تركز مرة تانية معاش تغلط مرة تانية ركز مرة تانية ركز خلاص مرة تانية ركز خلاص مرة تانية ركز مرة تانية ركز divide both sides by 0.5 divide both sides by 5 and then we take the ln both sides. This is to find the L. I feel better when يختار الجنة طالع من طيور الجنة برا سميك الشيخ طيور الجنة برا تو كيوت فور الشيخ. Okay, so wait, so what's the explanation for the I should read the question right? Let me read the question for the last one. So the question says, when optimizing the design for a cylindrical mailing tube in task 1, you are trying, okay. You are trying to minimize the errors for each optimization cycle. For each optimization cycle, after each cycle of optimization, the design error is 60% of the previous error. Huh? 60%, the design error is 60% of the previous error. Okay. For instance, initial relative error is 5%. After n cycles, En E naught multiplied by 0.60 to the power of n, the cycle, the number of cycles. Okay, I don't know how many cycles. Power of n, okay? Find the smallest integer. Find the smallest integer, n, so that the design error, En, is less than 0.50%. Show the inequality and logarithm steps clearly. So after each cycle of optimization, you're trying to minimize the error for each optimization cycle. After each cycle of optimization, the design error is 60% of the previous. Okay, wait a minute. It's only 60% of the previous error. For instance, initial relative error. So the initial, for instance, the initial relative error is like E naught. E naught. So the initial error is 0.5 is 5%. After n cycles of optimizations, unknown number of optimizations, En is equal to E naught, which is the initial optimization cycle, multiplied by 0.60, multiplied by 0.6, which is a 60% error, which is the 60% error design that we're removing each cycle, that we are removing at each cycle, to the power of n, which is the number of the cycles that we're going to be removing this percentage at, okay? And so decreasing the number of cycles that we're decreasing, okay? Find the smallest integer, okay? So we're trying to find the smallest amount of cycles, okay? The least amount of cycles integer, so that the design, okay, reaches an error percent of 0.5. So we want to decrease this in this initial to 0.5 basically. Okay. Show the inequality and logarithm steps clearly. To further improve the design, you introduce a boosting algorithm that reduces the error by 70% in the first 2 cycles and by 60% in each subsequent cycle. Compute the new minimum n to beat the 0.5% error. Each cycle takes time 20 minutes initially, but becomes 10% quicker per cycle. Thereafter, if you stop at the n cycles found in the stop at the n cycles found in the first part without boosting. Compute the total time Tn and then numerical value in minutes. I think I understand the question. A boosting algorithm that reduces the error by 70% in the first 2 cycles and by 60% in each cycle, in each subsequent cycle. Actually, I should probably put this on the side. It's gonna be useful. So let me see if I can make sense of this. So firstly, we have the initial amount of cycles is 5%. The goal is to reach 0.5%, okay? Or less than 0.5%, okay? Less than 0.5% error. So error percent. So the in order to do that, and so the equation to know the to relate, like, because we're trying to decrease it by 60%, so that's as per the question, as per the given, as per what's given. We're increasing by a factor of 60%, okay? It's going to be 60 at each, so like it's going to be 0, it's going to be 5 multiplied by 60 to the power of n, okay? To the power of n at each cycle. So the n is going to be the number of cycles, the 5 is the initial, and the goal is to reach until we reach 0.5, and then we stop, okay? Okay, until we reach less than 0.5, actually, not just 0. 0.5 or less, okay, and then we stop. A reduction rate is 60%, as we said. Initial time is 20 minutes, okay? 10% faster with each cycle, okay? So we need to keep that in mind. So firstly, so we know the formula. So 5, we take the 5%, which is the initial, and then we multiply that by the decrement, which is 0.6 or 60%, to the power of the number of the cycles that we're going to take. Quite simple and straightforward, okay? And then we make an equality. So since an inequality, so since we want to reach 0.5%, we put the 0.5% as our goal here. So this should become less than 0.5%, okay? Less than 0.5%. So, and then so we start solving the formula. We take this to the other side. So 0.5 over 0 is 0.1. 0.5 over 5 is 0.1. And in order to get the n, so we need to use the feature of the algorithm where we can take the n outside if we take the algorithm both sides, okay? So we do that, and now we take the ln of 0.6 and ln of 0.1. Clearly they're going to be negative numbers, so since they're negative numbers, we take them to the other side. Since they're negative numbers, when we take this to the other side without changing the sign, we have to flip the inequality, okay? So flipping the inequality, we get n should be bigger than ln 0.1 over ln 0.6, and we get the ln n is bigger than 4.5, okay? Bigger than or equal to 4.5, okay? Um, Okay. uh, okay, and then okay, so this is gonna be 5. And so in the if we look at the rest of the question, so to further improve the design, so we assume that we introduced an improvement to the design. Okay, so we assume that we improved an improvement to the design where at first cycle, at first 2 cycles, okay, the first 2 cycles, we can run for 70% instead of 60, okay? We can run for 70% instead of 60. And so since we already know the n, a boosting algorithm that reduces the error by 70%. That's 60% of the previous error. But this one just reduces the error directly by 70%. Okay. So reducing the error by 70%, meaning that we will only have 30% error. So we'll multiply the 30% by the 5% error that we already have. And we get a, so 30% of 5% is 1.5%. And then we run that for a second time and we get a 0.45%, which is which is less than 0.5%, right? Which is less than 0.5%. So how many cycles did that take? Only two. Only two cycles. So the number of cycles to n. So n is equal to 2. And to calculate the time, and lastly, each cycle takes up to 20 minutes, okay, initially, but becomes 10% quicker per cycle. Thereafter, if you stop at the end cycle found in the first part, okay, so the first part where we used 5, if we stop at the fifth n, so t to the n, so tn, the fifth n is going to be so if we start with the fifth n, so we're just gonna use the summation. So we have 20 plus 20 times 0.9 becomes 10% quicker per cycle. 10% quicker, that means we decrease it by 90%, right? Multiply by 0.9. Okay, so just like what we did here. So then we set up our series. We set up our series here. Series. So we set up our series here. And we see the 20 plus 20 times 0.9, and plus 20 times 0.9 to the power of 2 to the power of 3 to the power of 4, and we stop at the fifth. So this is a geometric series. We know that it's a geometric series. Sum. So s to the n is equal to a 1 over 1 minus r to the n 1 minus r. And so yeah, to just add this up, and to get the t we just 0.9, and to get the t, time required per cycle, per 5 cycle, per cycle. So no, usually it would be like 20 times 20 times 5, right? 20 times 5, that's going to be like 100 minutes. Since we decreased by 10% at each one, so using that decrement, using the series here, we find that, oh yeah, actually we ended up with 81 minutes or 82 minutes, yeah. Or you can say 82 minutes, yeah. Okay. Alright, alright, alright. Oh boy. Hello, my name is Yarub Al-Haj. This is a presentation regarding the assignment for engineering mathematics. I'm going to be presenting three main problems that were presented in this assignment. So the first one is about a cylindrical tube. So we are tasked to design a cylindrical tube for mailing A4 papers, and we are given some dimensions. So we're given the volume, we're given how much each side is going to cost. So before we get into that, so we know we need to basically optimize the cylinder so that it costs the least amount of money to make it. And how do we do that? We need to know the height of the cylinder, the minimum height, the least amount of height. Okay, so because the height has a cost, right? Or like not the height, like the side, yeah, the side has a cost. And the end caps also have a cost. So this is the cost of the end caps, and this is the cost of the sides. And so we want the least amount of square meters per each one of those to house the to house this volume. Okay, and in order to do that, we can come up with a function. But before that, so the area of the each side, to figure out the area of each of the end caps, it's just the area of the circle multiplied by 2, since we have two end caps. And then the area of the side is going to be the normal area of the side. So where is it? 2 pi r here, 2 pi r times h, right? And we know this from the cylinder area formula right here. And yeah, so besides that, uh, so we have these we have these information so far. And so we're going to create a function that tells us how the cost affects the sides per meter, you know. So we say that, okay, we assume that cost per meter side multiplied by the area of the side multiplied by the cost per meter of the end caps, multiplied by the area of the end caps. So we keep the area in mind for each one of these because each meter costs money here, right? So we want the least amount of that. So we multiply the cost here multiplied by the area of each of these, the side and the area of the side, the area of the end caps. However, we have some missing values here, so obviously we don't have the radius and we don't have the height. And those are the two main factors that affect the cost. And so we try to find the height first. So we have the volume. So since we know the volume, we can find the height easily. So, okay. And so so the height is equal to 0.010, which is the volume, divided by pi r squared. Okay, we just rearrange this formula. Okay, we took so it's just a normal equality, right? So we know that the v, we take this to the other side, and we take this to this side, so that we can find the h. Okay, next we rearrange that into the formula. So we substitute that back into the formula in order for us to have only one variable, which is the r. Now it's easier for us to find the r. So we still don't have the r, but in order for us to find the r here, we need to take the derivative, okay? We need to take the derivative of the r, and so of this function in general. And so to make it simpler, we replaced it from this form into into this form. Okay, so now it's kind of easier to it's kind of easier to do the derivation here. So we do the derivation, we get this 2 is multiplied here, and this should be 2. Okay, this should be 2. So this is 0.36 to the power r to the power of -2, and this is going to be -1 since the -1 goes here. And then after that, we bring it back to its original form. So now it's over r squared, and yeah, we got this. And then next, since we need to find the least amount of radius that we want, okay, the minimum amount of radius. So we use a stationary point rule. So we take the zeros of this equation. So we equate it to the 0, and then we take this to the other side. Now it's both of them are positive. Okay, so now we just try to isolate the r. So we just rearrange the formula here so that it's in terms of r to the power of 3. And then to get rid of the power 3, we just take the cubic root of both sides, and we get the final answer, which is 0.1 meters squared, which is the optimal radius. And so after that, since we got the optimal radius, now we can get the height. We just substitute back in the previous formula for the height, this formula right here. Okay, we substitute the r here, and we have the pi already, and we get the height, which is that. Okay, this is per square meter. Okay, and then after that, since we have the height, we have the radius, we can just substitute them both back into the original formula, and we get our C minimum, which is the minimum cost to spin. So we have the radius, we have the height, 10 centimeters in radius, roughly 31 centimeters in height, and 5.36 minimum cost, okay, which is in ringgits. Okay, so the next problem presents us with a billboard that is behind this mailbox. So this billboard is affected by the wind. So the wind is blowing on it with pressure. So we have these dimensions for this billboard, which are the width and the height, okay, which are extremely essential for us to calculate. And we have the pressure, a formula for the pressure here, and we have a formula for the force. Okay, so for us now, firstly, obviously, we need to, in order for us to find the pressure, um, and like the specific pressure that there's going to be applied, we need to find the force first, right? So the main pressure that we need to find is the center pressure. So to find the center of pressure, we first need to find the force, and then we need to find the pressure. Okay. So the force is represented by this given formula, and we just simply substitute the numbers were given. So we substitute the height and substitute the width here, and through that we just do normal integration, and taking the 5 outside of the integration, and then we integrate. So this is just the opposite of derivation. Normal things here. So to the over 2, and then becomes to the power of 2. 2 divided by 1. This is going to be 6. Okay, and this is going to be 2. Um, yeah, just normal derivation. Yeah, and then um, we get this value right here. So after we substitute the 4 and the 0, we get this value. So which is 1,280 Newton. And before we finish this, we need to find also the moment. So in order for us to calculate the pressure, so the moment is represented by this formula, which is quite similar. The only difference is that we have the y factor here. And so by using like this extra y in here. So we multiply it inside, and then we take the integral, right? So now it's a little bit different since we multiply the y inside. Now it's y squared and y power 3, right? And so we take the derivative. We take the integral of those. So it's quite simple. Same thing here. So like over 2 over 3, and then we simplify it, and then we get the integral. We substitute the 4 and the 0, and we get the final moment, which is 2880. Okay, so in order for us to find the pressure, the center point pressure, uh, we divide the moment by the force, and we get this center point for pressure. Okay, so to represent this, so like, what if we say that um, the YCP, okay, YCP, which is this, or the yeah, PY, which is PY, is equal to YCP. What is that gonna mean? So this is gonna mean that the pressure is at this exact center point. So the exact center point, this is the billboard, okay, for example. Okay. So the center point, we have the height of this, which is 4 meters. Okay. So the center point is at the center here, which is at the 2 meter mark. Okay. At the 2 meter mark, here, this is going to be the center pressure. But since we found, so if the pressure at the center is going to be divided equally at both sides here. But what we found here is that the center of pressure is not actually in the middle. So the center of pressure is going to be here, okay, somewhere at 2.25. Yeah. So at 2.25, this means that if we look at the billboard from the side, okay, if we look at it from the side, it's going to be a little bit tilted, yeah? So we're going to have the force being applied from the top here, a little bit away from the center. So this is going to tilt this to this side more than this, which is going to mean that the pressure being applied here at the top is higher than the pressure applied at the center. Okay, so therefore the pressure at the center, the center pressure, YCP, is going to be lower. Is going to be lower if YCP was equal to PY. Okay, and so this is quite simple and straightforward. And let's, oh, finally we have one more problem. So we're trying to basically improve on our first design for the cylinder, right? So our first design for the cylinder was good, but since we have developed more efficiency, more error decrement uh, function, so this error decrement function is going to help us to decrease the error of the design. Okay. So the givens here are the initial error, which is which is 5%, and then our target is to decrease the amount of error to 0.5%. Okay, or less than 0.5% actually. And then the reduction rate that we are given is 60%. And the time, okay, we're going to do this later, so the time is like 20 minutes and 10% faster each cycle. Okay, so what does this tell us? So this can help us formulate a formula. So we know that the initial pressure, and we know the target, and we know what are the factors that we're decreasing by, right? So we know that the initial is 0.5 is 5, okay, 5%, okay, and we're going down by 0.6 0.6%, but we don't know how many times are we going to go down until we reach, and this needs to be less. This needs to be less than 0.5, okay? And for this to be less than 0.5, we need to know how many times we need to reduce the 5% by 60%, okay? So this is going to be our n. So we need to figure out the n here, right? And so that's exactly what we did here. So we got the inequality, and then we basically divided both sides by 5. So we got 0.1 here, and then this, and then we took the special algorithmic rule. So we took the ln of both sides so that we can take the n outside. So using this specific feature of algorithms, we were able to separate the n on its own. So we put it in this side. After taking the logarithm of both of these, we found that they're both negative. So taking this to the other side will flip the sign, the inequality, if we don't change the sign. So we didn't change the sign, we took it to the other side, so we flipped the inequality, and we got a number of 4.5, right? So 4.5 is not an integral number, so it's not an integer number. We need an integer number, okay? So this is roughly is equal to 5, right? So we can round it up to 5. So we take the number, the n, number of cycles as 5. And so we suggested that in the first two cycles, okay, in the first 2 cycles, we actually are not going to use we're not going to use 60%. We're going to use 70%. Okay, 70% decrements, which is going to be 30. So instead of so we basically just multiply by 0.3 directly. So we take the 5% again, multiplied by 30. So basically take 30% of the 5%, which is 1.5%, and then we take another 30% of the 5%, and we already get the 0.45%, which is already lower than the 0.5, which is the target. So we have reached the target by the first 2 cycles. So that gives us a number of cycles of 2. And so next we need to calculate the time. So the initial time is 20 minutes, but 10% faster each cycle, okay? So at each cycle, at each of these 5 cycles, we get 10% faster, okay? That's how the time works. So we have 20 instead of 100, so 20 times 5, that's going to be 100 minutes, okay? What if we decrease at each 5, okay, at each cycle, we decrease by 10%. We decrease this 20 by 10%, okay? Decreasing the 20 by 10%, so this is going to be 100 minus 10, so this is going to be 90%, okay? So we multiply the 20 by the 90%, as we represented it here. And so we put 5 cycles. So we got the first, second, third, fourth, fifth. And then this is obviously a geometric series sum. So we just use the geometric series sum rule, and then to add them all together, and we get our time in minutes, 81.90 minutes, which is the time that it's gonna take instead of 100 minutes, since we decreased by 10% at each cycle. And yeah, that was everything for the assignment. Thank you so much for paying attention. And yep, my name is Yarab Al-Harsi. I'm E230 4307.